Hi everyone, this is Matt Whitbread. This is my presentation on our midterm restaurant forecasting project that we all did. I'll spare you the goal. I think we all know what the goal of the project was to do. Essentially, just forecast the number of visitors going forward for about I think 39 days for about 800 plus restaurants in a particular database using time series model. So I'll skip all the nitty gritty on that and focus more in terms of the data, how I looked at the data, and then ultimately how I decided what model I would use and how I applied that model to get the forecast that I used to the upload into the Kaggle for the competition thing. So from a data description standpoint, the data came in a number of spreadsheets or data dumps, so to speak. But really, there was two general formats for how the data looked. The first was time series. So it was looking at the number of visitors, the number of reservations each day for each different restaurant. And then complementing that was some data that I call kind of characteristics data, which was things like genre, cuisine, and such things as locations. From my standpoint, the way I looked at this is I didn't find a lot of value in terms of really pulling out the characteristics data. I wasn't able to really build any models that was able to really overlap a time series with also using, you know, um, basically characteristics data like you would in a typical linear regression. And I have a lot of luck with that. So I thought it made more sense to focus more on the time series because I thought that that's really where the kind of the information was coming for most of this stuff. So from the slide I'm showing here is two different charts. The top chart shows the aggregated visitors per day from within the database. This is a combination of the AIR database and the HPG database. So every day, this is the total amount of visitors according to those two databases. So one thing in particular jumps out of this as being problematic, and that is the fact that on, I believe it was July 1st, which we can see right in the middle of this graph, the amount of visitors went from roughly 5,000 up to 15,000. So basically triple. So that to me tells me there's obviously something wrong with the data. My guess is that either restaurants came into the database on July 1st or they just fed more data in on July 1st or something along those lines. So in order to solve for that, which is because it's clearly problematic, I adjusted it to take the total aggregate visitors from the restaurants and then divide it by the number of restaurants in the database. So kind of a same store sales measure. And that's the chart you see or the plot you see below. So we can see within this perspective that the trend now is much more in line, or I should say, is more consistent through time. It has its ups and downs. There's obviously seasonality, which we'll talk about. It's on a weekly basis, but this chart makes a lot more sense. So this is the data that I use going forward. This is the data I use to build out the models, to test the models, and to try to get a handle on which ones made more sense. So this is the decomposition, the simple decomposition on that first um, non-adjusted data set, I'll call it. We can see that the data jumps over the July 1st. The trend goes from steady state, all of a sudden spikes, then continues. And the seasonality is just crazy. We're looking at 4,000 to less. So it's crazy swings in terms of the seasonality when you look at it from this basis. You contrast that to this when we adjust the data, we can see now the seasonality makes a lot more sense. It's roughly plus or minus 9 people on average per restaurant that goes from the lowest to the highest in terms of the weekly fluctuations. The remainder is obviously much smaller, and the trend is much more steady. So, it's just a case really for using the adjusted data within here. This plot here, this shows the basically the seasonality. This is the weekly seasonality. So not surprisingly, we can see that on Friday, Saturday, and Sunday, we have more on average, a lot more visitors or people going to restaurants as opposed to Monday through Thursday. So this is the seasonality that we're dealing with. It's on a weekly as opposed to a monthly, quarterly, or annual basis within this data. But this is the seasonality we're trying to incorporate within our models. So what this is this is a summary in terms of the statistics that I used in order to select the different models. But starting with the types of models, I use 5 different types of models: an ETS, ARIMA, STL, a few different flavors of the whole winter model, and then something called TBATS, which we haven't quite covered in class just yet, but the literature suggested that this was a very popular method to be using for a daily data. It's a bit more complex than these other ones, so I started from simple and then got to a bit more complex. Looking at it from the root mean squared error perspective, you can see that the t-bits actually performs quite well. It's got the lowest RSME, followed by the STL, and then everything else is kind of, broadly speaking, in the same kind of group in terms of that. I included the linear regression in terms of what the statistics were from the accuracy table, but by and large, this really isn't a very useful model to look at. I really just regressed the day of the week along with the holiday flag, and it just got very poor results from linear regression. So I pretty much scrapped that idea and stuck with the time series models. The AICC table, interesting that it shows ARIMA is by far in the lead versus the others. The others seem to be all right around the 35 to 3600 range, while ARIMA seems to do very well. So that surprised me. And so what I wanted to do is a bit of a tiebreaker here. So I did a cross-validation measure, and this is on a subset of the data because there's a lot of computing power that comes along with this. So I did a cross-validation on 4 models: ETS, ARIMA, STL, and TBATS. And that window, I believe, was around 7 months long. And interestingly enough, the STL ended up outperforming the rest of the models compared to the ETS and STL. And interesting, the TBATS model did terrible on a cross-validation basis. So not only was this a tiebreaker, but I also thought it was a very interesting look in terms of what models would do best on out-of-sample data, i.e. for forecasting. So that was my process in terms of evaluating the models. I did it on the aggregate data, and then from there, I opted and I chose the STL model, and I used then an STL, an iterative process. I built a loop within R that looked for every restaurant. It took its individual time series, ran an STL model within that, and used that to predict the amount of visitors for each individual restaurant, and just did that all the way through. So I thought that was the only real way to do this rather than use common parameters similar to like an ARIMA model. I allowed the STL to basically just model it. I think it was the MSTL function, was to model each individual restaurant and then create kind of what I consider to be a customized or unique prediction. So that's it. That's kind of the whole process in terms of what I did. Fun project. It was really interesting, and I hope you enjoyed the presentation.